All right, go ahead and write this problem down, and then let's work on dividing these rational expressions. When I've got a division problem, like I do here, I want to convert that to a multiplication problem. So I can just multiply right across the numerators and multiply right across the denominators. In order to convert a division problem to a multiplication problem, I just need to take the reciprocal of that second rational expression, right? Just swap the numerator and denominator. So when I do that, I'm going to come up with this. This very first component will stay the same. That's x squared minus 36 in the numerator. I'm going to use a few different colors here to keep track of things. The denominator is going to stay the same also in this first expression. But now here, instead of having a division problem, I've got a multiplication problem here. And in the numerator is going to be what used to be in the denominator there. That's the 5x squared plus 10x. And then swapping the numerator to the denominator, that'll be the 20x cubed. So now, one by one, we want to try and factor as much as we can and cancel out some common factors if we can. So let's start and go ahead with the blue term here, the x squared minus 36. That format looks familiar to me. I know that 36 is a perfect square of 6. So this is a difference of squares. I'm going to use that factoring pattern to rewrite x squared minus 36. If you don't remember the difference of squares, when we've got an a squared minus a b squared, right, that can be rewritten into factored form as a minus b times a plus b. So here my a value is really just x. So I'm going to rewrite this factor as x, and my b value is 6. That's the square root of 36. So x minus 6, x plus 6 becomes the factored form of x squared minus 36. All right, let's take a look at the denominator of that term. And this looks like just kind of one of those standard sum product ways of factoring here. So let's set it up where we've got our x's, and we now need to come up with two numbers that multiply to 12 and that add to 8. So 6 and 2, those multiply to 12, and when they're both positive, they add to 8 those. So that's how I'm going to factor that one right there. All right, let's go ahead and factor the green term here. And for this one, I notice that there's a greatest common factor. I can take out a 5x from both of those terms, and when I do, I'm left with x plus 2. So that's a good way to factor that one. And then the very last term, I don't think I can factor at all, so I'm just going to leave that as 20x cubed for now. So now comes the fun part, I think. We can just compare the numerators and denominators. And, when you multiply something, you're just multiplying straight across the numerator and denominator. So we've got a nice big fraction here. I see x plus 6 in both the top and the bottom. I see x plus 2 in both the top and bottom. I see a standalone x here. What can we do with that? Well, I see one thing I know is that the x cubed in the denominator, I can rewrite that as x times x squared. And then it becomes really easy for me to cancel an x from both the top and bottom. I can kind of do the same thing with 20 here. I can rewrite 20 as 5 times 4, and then it looks like I can cancel 5 from both the top and bottom. So I think I've done all the canceling I can now, and what am I left with? Well, not a whole lot, which is good. We've simplified this thing quite a bit, and what we're left with in the numerator is x minus 6, and in the denominator we have 4x squared. One last thing to think about, what are the restrictions on the domain in this kind of problem? Well, to that, we're going to first look at the two denominators in the original problem. All right, and we want to find what are those x values that would make those denominators 0. Well, in this first one here, let's see, we ended up factoring as an add x plus 6 and x plus 2. So an x value of negative 6 would make that denominator factor 0, and an x value of negative 2 would do the same here. Now this original denominator, 5x squared plus 10x, actually I'm going to highlight with a different color, that actually turned out to be the numerator once we swapped things and converted it to a multiplication problem, but we still need to check it. So what x values would make that 0? Well, an x value of 0 and an x value of -2. And lastly, we do still need to check whatever our final denominator was after we did the reciprocal conversion to multiplication problem. And here it looks like an x value of 0 would also be. So factoring all these together or taking them all into account together, it looks like we cannot have an x value of -6, -2, or 0. These are duplicates, so we don't have to worry about those. We can rewrite this problem as x minus 6 over 4x squared, where x cannot equal -6, -2, and 0.